The next example we will look at for a hypothesis test with two sample means is a situation where we have actually data from the sample instead of summaries. A professor at a large community college wanted to determine whether there is a difference in the means of final exam scores between students who took the statistics course online and students who took the face-to-face statistics class. The professor believed that the mean of the final exam scores of the online class would be lower than that of the face-to-face class. And we want to find out if the professor is correct. So randomly selected 30 final exam scores from each group are provided here. We have the online class as our population 1, let's say. And we have the face-to-face class as population 2, let's say. And we want to know if the mean of the final exam scores for the online students is lower than the mean of the final exam scores for the face-to-face students with an alpha equal to 5%. Remember, the null hypothesis is that the two means are equal to each other in terms of one variable, the difference. Online minus the mean of face-to-face will equal to 0. And we want the alternative hypothesis to be that the mean of online will be less than the mean of face-to-face, with population 1 being online. So in terms of one variable, mean online minus the mean face-to-face to be less than 0. This will be a left-tail test. We will use a t-distribution because we don't know the standard deviation of the populations. And as a t-distribution, as you sketch it, remember that it is more spread out than a normal distribution. The variable that the values are shown here in the bottom are t-scores for the difference of the two means. The mean of online minus the mean of face-to-face. And we want to use the app for comparing two means. We want to enter data and choose provide your own. The response variable is the exam scores. The group 1 will be online students and group 2 will be face-to-face. And here, if you have an Excel document or a table data document, then you can just paste them in ArtofStat and highlight the second group, copy and paste it in ArtofStat. And I want to do a significance test, and I want it to be a lower tail, a less than, and I need the null value for the difference to equal to 0, so that the difference is equal to 0, meaning that the two means will be the same. And you will see here that ArtofStat tells us that these were 30 online students with a mean of 72.85 and a standard deviation of 16.92. The face-to-face are also 30 students, mean of 84.98 and a standard deviation of 11.71. The null difference for the means is 0. The observed difference is 72.85 minus 84.98, which is negative 12/13. So the observed difference is the x bar from online minus the x bar from face-to-face, negative 12.13 points. And the standard error comes from the complicated formula. Here it is 3.76. That's the S of the x bar online minus x bar face-to-face. And it is 3.76. The degrees of freedom, again, very complicated formula. is equal to, I don't see it, so let's select here to show the degrees of freedom, 51.6. Notice here that you get a very different title for that box compared to older versions of Art of Stat if you have used it before. So 51.7.6 is the degrees of freedom. Since you have a test statistic, since you have an observed difference that is negative, you expect your test statistic to be negative. So you have a test statistic t-score of negative 3.229. And this is approximately here. Remember to sketch in your graph and also shade the area of interest. You are looking for differences between the two samples to be at or more extreme values than the one that you found. So at the test statistic negative 3.229 or further away from the mean of 0. And the probability of having such a result is 0.0011. Notice here how Art of Stat also sketches it for you and shades or indicates the shaded area, which obviously is very small to see. So p-value 0.0011 is the area here, 0.0011. So as you can see, the p-value is less than alpha, and alpha is the level of significance which permits us 5% of the times to have an error in our hypothesis test or to have selected extreme samples. So the decision for that, since you did end up with a difference that was more unlikely than the expected confidence, then you can say that we have enough evidence to reject the null hypothesis. So remember in your decision to always talk about whether you are rejecting the null hypothesis or fail to reject the null hypothesis, and in your conclusion to say that you have evidence to support the alternative or not support the alternative. So since I have evidence to reject the null hypothesis, that means that I have evidence to support the alternative hypothesis. At the 5% significance level, the sample data provides sufficient evidence to support the claim that the mean exam scores of the online class were lower than the mean exam scores for the face-to-face class. The last topic for section 9.1 of our OER statistics course that we want to look at is Cohen's standards for small, medium, and large effect sizes. It's called Cohen's D, which is a measure of effect size based on the differences between two means. Cohen's D is named for United States statistician Jacob Cohen, measures the relative strength of the differences between the means of two populations based on sample data. It is the difference between the two means divided by the pool standard deviation. Remember we mentioned in previous videos that we will be looking at the pooled standard deviation for the difference of two means. This is a little more complicated formula, but this is what it looks like. And Cohen's D equals to the difference between the two sample means divided by this pooled standard deviation. The reason is that the difference of the two population means is assumed in the hypothesis test to be 0. So, for example, let's assume that we have a population alpha A from which we took a sample size of 25 found the mean of 5 and a standard deviation of 1. And we have a population B where we took a sample size of 16, found a mean of 4.7 and a standard deviation of 1.2. Is the size of the effect small, medium, or large? Now, Cohen said that a small d would be approximately 0.2 and a large d will be approximately 0.8. A small d indicates that there is not significant difference between the two population means, and a large d indicates that there is significant difference between the two population means. So if we find this d value to be close to 0.2, then we can conclude that there is not enough evidence to indicate that there is a significant difference between the two population means. If we find a d to be close to 0.8, then we will say that we have enough evidence to say that there is a significant difference between the two means. Now, this was because in the past there was no technology available, and this was a very quick calculation that could be done more easily than a full hypothesis test. So let's try to determine the numerator and denominator of this d. The numerator will be the difference of the two means, which is 5 minus 4.7, and the denominator will be the square root of n1 minus 1, that will be 25 minus 1, which is 24, times the standard deviation squared, which will be 1 squared, plus n2 minus 1, that will be 16 minus 1 is 15, times the second standard deviation squared, 1.2 squared, divided by 25 plus 16 minus 2, and that will be 39. So the numerator is a 0.3, the denominator is the square root of 45.6 over 39, which is approximately 1.0813. And this d comes to be approximately 0.277441. And because this d is very close to 0.2, then we say that this is a small effect, and therefore there is no significant difference between the means of the two populations. So write your conclusion here when you do your notes. There is not significant difference between the means of the two populations.